I mean, that's the usual problem when you actually try to show something live that like actually runs, and then everything crashes, and you reboot your computer really, really quickly before the session starts. Okay. So I used to have a QR code there, so you could just like directly run things live as we go through this, because I mean, obviously nothing is more fun than me it's like seeing me struggle in front, but also telling me like all the things that will crash when you run it on your machine. So you could try to go to like a tinyurl.com/PyTrilinos2 and run all of this like Trilinos like in the cloud. So this, you can do this on your phone or wherever, and it should work. I mean, the interface might be clunky, but this should work. Right, I mean, should is the word. So I should talk a little bit like why we want a Python interface. So it's on one hand just as sort of like a coupling layer between Trilinos and other sort of like codes that are like out in the world that now all use Python or some other like Python compatible layer. So I mean, you could think like everything that's an LLM or some sort of like more modern AI thing, then yes, you definitely want a Python layer to like be able to couple to that. We also think that it's good to have a Python layer just to sort of like catch people leaving grad school where they are. Probably everybody coming from grad school now knows how to use Python. C++, maybe less so. And so trying to like get people sort of like onboarded in a sort of more gradual way. Let's see if we can get them with Python instead of like directly hitting them with like a compiler in C++ and all of that. Now, this is not the first try or the first attempt that we have had at having a Python interface for Trilinos. And I mean, we've learned a lot from the previous interface, but it was sort of like a hand-generated, hand-coded interface to functionality in Trilinos. And that works well on a sort of like a header by header basis, and you can do that, but you need a lot of buy-in from the individual package developers when they change an interface, that they also then change the Python exposed interface. Otherwise, nothing compiles anymore, and everybody just complains about your package. And so what we've gone for now is a sort of automated generation of Python interfaces for Trilinos. This is nice because it can adjust to all this configurability that we have in Trilinos, even if you have some configure option, and maybe this is not a great idea, but it happens in practice. People change the interface to their software depending on how Trilinos is configured. This is a terrible thing to do for lots and lots of reasons, but it happens in practice. This tool will be able to handle this. So we'll sort of like step through, and I'll show an example from how do you use this then to like solve a linear system using Trilinos, because I'm a solvers guy, but a lot of this stuff has nothing to do with solvers and could be like rolled out to a lot of the other packages in Trilinos. All right, so let me sort of like step through this, and I hope if at some point somebody actually like tries to do this on their phone, they can let me know if it actually worked for them. On the outset, I mean, we're just using standard tools here. We're not like reinventing anything. So we're going to use a PyBind 11 interface to Trilinos. And so if you haven't seen this before, it's sort of like really quite simple. So let's say that this is our C++ function that we want to like wrap in a Python interface. And really all that we need to do is we include a PyBind 11 header. Here's the function that we want to like wrap, and then we expose it as a Python module by just like declaring this module here and saying how this particular function should then show up in the Python interface. And I mean, obviously you can do all of this by hand, but it's just very annoying to do this for a really large code base. And so what we're using is a tool called Binder. And what this does is that it essentially pulls in all your code base and uses LLVM to parse it, and then tries to auto-generate interfaces for all the things that it finds, which obviously also has like its own problems. So you have to sort of guide it a little bit, like what are the things that should be exposed, what should be wrapped, and what should immediately be like left out and be ignored. So there's sort of like a whitelist, blacklist sort of thing going on where you say like, okay, these are the things that I really want like exposed in my interface, and these are the things that you should ignore. So as an example here, I'm showing, okay, the header files that we're exposing for tpetra, which is the linear algebra package from Trilinos, we're just pulling in all these sort of auto-generate explicit template instantiation files for tpetra. We're pulling them in, and these are the ones that Binder will run over and use to discover what tpetra actually is like, and what objects are there in tpetra, and what things could be wrapped. And then in the second step, we have our configuration file, and this is sort of a lengthy file, but so I'm just sort of like grabbing out a small portion of it that's relevant for tpetra, and that essentially is just saying, okay, we want the namespace tpetra to be wrapped on the Python level. We have a couple of sort of specialized functions that we will tag on. Can you read this in the back? Yeah. Okay, then maybe let's see. Can I do this? Yes. Let me see. Control plus. Yes. How about that? Better. Okay. Let's do that then. So I'm just showing the tpetra relevant part of this configuration file. So the second part is add on to Binder. We're just injecting some sort of special code that we only need on the Python level for tpetra. Doesn't really matter what that is now, but you can sort of like tag on things or subtract things through this configuration file. There's also a couple at the bottom here. There's a couple of classes that we just say, okay, these are implementation details. We really don't care to see them in the Python interface. Users don't need them in practice. And that's really all it takes from a sort of like bird's eye view. In practice, there's like loads and loads of like small little issues, because I mean, essentially, there's certain features that you cannot represent at the Python level that C++ has. So one example that we're still struggling with is, say you have a function that passes some small type, like a double by reference. In Python, doubles are immutable, so that's something that simply will never work at the Python level. And so you have to sort of like construct weird things around that, and essentially construct an object that is mutable around this little double, which is sort of like unpleasant.
How do you handle the difference between public, private, and protected functions? Does
PyBind will ignore like the private stuff. All right, so this is in principle how we generate all of this, and let's actually look at what you can then do with it and how you can use it. So I'm showing linear solvers. This is not, I mean, the whole process works for anything else in principle in Trilinos, but I like linear solvers. So let's see. So we're going ahead and importing tpetra, which is the linear algebra package from Trilinos. And I mean, one of the goals that we had also was that all the API sort of like matches one-to-one between C++ and Python. We already have like little enough in terms of documentation for our C++ code. We don't need to confuse users by now having a totally different interface. We want everything to be as close as possible between the two languages. All right. So we have imported tpetra, and now, I mean, if you have seen tpetra before, everything is nicely templated on the scalar type, so float or double or complex double, in which the computations will happen, and then a couple of like ordinal types, and then the node type, which effectively captures the Cocos execution space and memory space. Now, problem is, in Python, there are no templates. So what PyBind or like what Binder will do is that if you have something that looks like this in C++, some templated thing, it will generate a class in Python that effectively just concatenates everything into this very long name string that, I mean, yes, you can work with that, but it's not really pretty or useful. You don't want to like have to write code that uses that. And so we've sort of like added on some sort of small features that allows you to access this in a more sort of like Trilinos-like or like a C++ like way, which allows you through the through this access method to effectively then specify your template parameters in a way that looks a little bit more like C++. And that obviously they can then also handle default types, so you don't actually have to specify any of them. You can just specify the ones sort of like starting from the left that are non-default. And so it becomes a lot easier to like write code that looks very similar between C++ and Python, despite these template arguments. All right, so let's say we actually like want to like solve a linear system. So we need to first set up a linear system. The way this works is that in TPetra we first need to like specify how the data is distributed. That's called this map object that we already have started seeing here. If you want to like see help for all of these things, you can also just call the Python help function. It will try to mirror the doc strings from the C++ object and just include them directly. So let's see. Well, all of this now runs using MPI. So this is MPI for Py, which is sort of like the Python equivalent of just your plain, or the wrapper around MPI. And we'll also import Trilinos, which is all of this basic package that exposes a couple of like parameter lists, which is sort of like a Python dictionary for setting parameters. And these are all the sort of like basic components that we'll need to set up our linear problem. All right, so we'll set up our linear problem. We create a map. You notice here, this is the Python way of saying we're passing in no parameters whatsoever, which looks somewhat clunky, but that's Python. This will create a map, or this now essentially gives you back the templated map. So this is the map type. And then we can actually call the constructor for this map type and create our map. So this is a description or like a distribution of data over our MPI ranks. And we print this out immediately, just like verify that what we did here is looks sort of reasonable. Okay, so we have 1,000 unknowns. Okay, let's continue setting up a problem with that. If you have looked at some TPetra code, this looks very similar. We create a matrix, we're passing in a map, and then we're sort of like looping over the rows of the matrix and filling them one by one with insert global values. Could you do this more efficiently? Yes, of course you could. You could also, I mean, none of this will run on GPU at the moment. This is a pure CPU implementation. But I mean, the GPU ready implementation or access methods of TPetra are wrapped in the same way. So you could totally do that. All right, so we call this function, we set up our linear system. We also set up in the same fashion some vectors. We initialize them to 1 and 0. And then we also set another vector up just for a residual and compute our residual. And we check that, yeah, at the moment that's not 0. So we haven't solved the system just yet. All right, so we want to use some solvers from Trilinos. And one really nice way, and we've heard about this before, is, I mean, there's all these different packages for linear solvers. There's direct solvers from Amazos2, Krylov solvers from Belos. There's these simple sort of algebraic preconditioners or incomplete factorizations from IFPEG2. There's algebraic multigrid and Mueller. All of them are exposed in sort of like through a generic interface. This is called Stratamikos. And this abstract linear algebra interface called Thera. So let's just import them as well. And then we can go through sort of like a basic solver construction step through Stratamikos. So the way this works is we create this sort of like templated linear solver. It's templated on the scalar type as well. And we can then pass in parameters to tell it like what kind of solver do we actually want and how should this solver be parameterized. Well, okay, let's start off with a direct solver. That's really the easiest possible thing we can do. It takes exactly one parameter to achieve that. We have to tell it like, okay, what type of solver do we want? We want a linear solver from Amazos2. That's the direct solver package. We can print that out, okay. And then all we have to do is like set it up, pass it in, and construct our inverse to our matrix A that we pass in here. And now we have a solver. So let's make sure that our solver actually works as a solver. So we'll just call the solve routine from that solver object on our vectors that we've set up just before. And well, it tells us that it converged, which is probably a good thing for a direct solver. And we just double check that we actually solved the linear system here, and well, great. Okay, we're now at 10 to the minus 10, which is probably as good as being solved. That's good. So, and through this sort of like through these basic steps, you can get access to the vast majority of like linear solvers, preconditioners in Trilinos. So it's really all these. I mean, from Python level, this is fairly straightforward, and it really doesn't take a lot of work. And you can obviously couple this to like other assembly code and just then use Trilinos solvers. So let's get into some other solver options that we have and just try to exercise them. So maybe a good thing is let's figure out what's actually available at the moment. And so what we do is we just print out what's available in terms of linear solvers, and then also for the different packages, what these actually expose if you give them a bit more information, if you ask for a specific solver within those packages. And so at the moment, what you can get access to is in terms of linear solvers, that's Amazos, so direct solvers, and Belos, which is all the iterative solvers. So think CG or GMRes. If we then query like what's available within Amazos, currently there's interfaces to KLU2, which is a sparse direct solver, but there also is an LAPACK interface in there that you can use. And if this were actually a GPU build, you might also get some sort of like vendor-specific direct solver packages through that. From the Belos side, so we have a long list that I'm not going to read of iterative schemes that you can use. But I mean, essentially, if you want something like GMRes, CG by CG step, you can pull it out of there. Preconditioning at the moment, what's enabled here is none. That means, yeah, you don't do any preconditioning at all, or IFPAC2. These are all these sort of like simple algebraic sort of like one-level flavor types of preconditioners. And there's an even longer list in there. Jonathan introduced a lot of them like earlier on in his presentation, so I'm not really going into the details for that. Just to show that this works and why we tend to have like really long parameter lists when you like use our solvers. Here's an example of using a CG solver. So from Belos, we're setting all the sort of like convergence criteria up that we want for this solver. So this is this first block here. We can choose how much output we want about the solver, if we really just want to like see that in the event and it converged, or do we want some sort of like progress update. And then we set up a really simple Jacobi, so think a diagonal preconditioner for the preconditioning of the system. And then, well, we can print out that all of this like nicely went in, and we repeat our steps of passing this parameter list into our solver factory, constructing the solver, using the solver to solve our linear system, and then in the end, well, this time we get a little more output. Actually, that something happened, something iterated, and in the end we actually see that it doesn't think that it actually converged. Well, that might be due to the fact that we used a really, really simple preconditioner, so maybe we need something better than that. That's okay, maybe that's to be expected. So let's get something better then. So something better is always multigrid. And so multigrid in Trilinos now means MULU. And so we will enable the MULU preconditioner in Stratamicus. It's not default enabled, and we should probably work on that. And we'll go through like very much the same steps again. We'll use a Krylov solver, but this time we will set up a even longer parameter list. Oh, actually, no, we use all default parameters. Great. So MULU is much easier to use, clearly. So we'll set up a multigrid preconditioner for the same problem as before. So this is still our 1D% problem, but we'll get a lot more output. So as we run this, same steps as before, we just zero our solution vector to be sure that we didn't just carry our solution forward. And we get a lot of output of what MULU is doing. It's creating a, let's see, a 3-level hierarchy. Great. And then when we solve the system, it solves the same thing now in 7 iterations. Okay. I mean, this is not really like me trying to plug a multigrid here as the perfect solver, but I mean, keep this in mind. All right. Now, one of the nice things is also that you can like seamlessly combine this with other tools that might be maybe more appropriate for visualization. I mean, you can obviously like use all the cool ParaView tools and whatnot, but if you want to sort of like do this sort of like in a tight loop and sort of you're still developing, then maybe it's nice to do all in one place. And so, well, we can just use Matplotlib and like visualize what our solution now looks like. And these are all sort of like a standard tpetra access methods. So what we're doing here, we're getting the local data view out of this vector, which is a Cocos view. We're asking it give us this thing on host, and we only want to read it. We can print this out. It also gives us this object or like this class in this like slightly annoying format with like everything being concatenated into one really long class name. But we have all the access methods to like then directly cast this into a NumPy array or into a torch object. Yes. Yeah. Yeah. So you can, in principle, use this to like really easily like couple together things from the Python world with all the cool things in Trilinos. Okay, so what I've shown in this notebook, I mean, you might have seen in the beginning, I created like an MPI communicator, and I didn't specify how many ranks or anything, and that was because it was a single rank. So doing multiple ranks in a Python notebook is a little bit kludgy and not really like, this adds too much overhead, but I mean, all of this works with MPI. It works with different backends, so you can, I mean, all of this was CPU. You can run the same thing on GPU. Obviously, the same sort of like caveats apply. I mean, you can't like just like access the GPU view like on host. I mean, you will get errors, but these are the same errors that you would get at a C++ level. So you have to have some understanding of like what you're doing. It's not like magically Python, everything works great. I will also say that currently what I've shown you is sort of like Python running on the outside and then like running things at the C++ level on the inside. But it doesn't have to be that way. And so I'll try to see if, I mean, my computer crashed early. Let's see if that still works, if that still comes back. Okay. So this is the same sort of server. Let's see. You can also do the thing sort of like inverted. You can like run your C++ code, and then on the inside just launch the Python interpreter when you actually need it. Let's see if I can talk and type at the same time. Oh, perfect. Should have done this way earlier.
My true calling.
Thank you.
Let Siri start dictating.
Okay. This is a really, really short example. So this is just to show that we have our like little bit of like our teeny tiny C++ driver. All we're doing is we're creating like at a C++ level some vector, some tpetra vector. We're initializing it with some value, printing it out, and then we're launching an interpreter. And here I'm directly like injecting, or like I directly included in the C++ source code like what the Python code is. You could totally read this in from a file. So the way that we sort of like, or I sort of imagine that this could be useful is, I mean, we have a lot of cases where analysts try to like specify like some like boundary conditions or initial conditions for like a solve using, at the moment, something in Trilinos which is called RTC, which is in PAMGen, which is sort of like a made-up little like domain-specific language to like set boundary conditions or initial guesses. But this is sort of limited. It always runs on CPU, and you need to learn this language. But people already know Python, and you can totally like write Python code that like runs on CPU or GPU or wherever. So you could totally use Python here as a drop-in. Everybody coming in will automatically know from the get-go like how to like set the initial conditions, and they can do it as efficiently as they want. If they don't care about performance, just do it on CPU. Just do it like in NumPy style. If you want something a little bit more efficient, then maybe you go to PyTorch, and then you can run directly on a GPU. And I should say the sort of like access methods using NumPy and PyTorch, they don't do any deep copies. So you're accessing the same memory all the time. The other thing that this sort of thing allows you is that, say you want to include some, I don't know, some neural network or some LLM code directly into your big, massive C++ code that you already have. This now directly allows doing that. I mean, you obviously, I mean, you could do all of these things in C++, but I'd imagine that it's a lot easier to find documentation for your favorite LLM or whatever out in Python. So with that, I'll just leave it. I hope I didn't go over time. And yeah, thank you for your attention.
So Cocos has its own Python work. Are you integrated with that? Is there any collisions, or how does?
At the moment, no, but I mean, we can ttotally interface to that. I mean, in the end, it's just essentially you need to like pass the pointer into the correct spot and like then create like a PyCocos view object instead of like creating something that lives on, like it comes out of like PyTrilinos. But this is really, I mean, yes, we can add that. So far, we really haven't done this because it's like one additional dependency that is at the moment not really necessary. But if that's useful, then yes, of course.
Yeah, I'm just thinking if you use their Cocos to create a view and then initialize the tpetra with that view.
Oh, I mean, it would totally come back and be fine. I mean, it's, yeah. Yeah.
So you said you want to basically get the people that come from the university where they're up. But what you basically did is you injected types into Python, which is something that Python doesn't like. And Python people will just strangle you for that. But what you basically did is, if you think about it like from an abstract standpoint, you basically did just switch from C++ to Python. But if you
Yes.
would just put auto wherever you would need to type in Python, you would get the same thing in C++.
Okay. I think there's still something to be said for speeding up development cycle. Because yes, you can put auto everywhere, and then you like fight through like all the compile issues, and I think the development cycle in Python you can significantly speed things up. I would also argue.
I would disagree. I would say the using cycle, that is something you can speed up, because just using stuff that works in Trilinos, you bind it once, it's compiled once, you use it for different matrices. Everything's fine. Now imagine you want to change any function inside Trilinos. You will have to recompile.
Oh yeah, no.
Bind everything.
I totally agree. I mean, this is not a Trilinos development tool. This is a tool for developing applications built on Trilinos.
With that, I would agree, yeah. But still, I'm curious. Like, I'm a PyCocos developer too. So the feedback we get the most is we don't like types. But there's no good way around it.
Right. I mean,
So
you're not going to solve that.
There is nothing you can do if you use C++ to get rid of it. But one other thing that touches on what Roger was saying is, like, since Cocos now has MD-span as its main abstraction, it would make sense to have a lot of this data interop on MD-span, basically. Because right now, I mean, you're doing it, but every other library would have to redo this and wrap their own stuff in Python. If
Oh,
you
yeah.
just need data exchange, this could be just a quick way to solve it once for basically everyone.
Oh yeah, I totally agree. I mean, I also have to say this is still very much work in progress that we're sort of like chipping away at every now and then. But yeah, I agree.
There's someone else a question, because I have more. All right, then.
Go for it.
Could you go back to your previous notebook? The other two things? Because when you asked, I think it was if pack2, what is available? This
Yes.
list had a ton of duplications. Like, for example, if you look at the second line from the second to last section, banded relaxation. So
Oh.
identity. And,
Okay. This is not a Python problem or a PyTrilinos2 problem. This is an if pack2 problem then. Yes.
so these are really different.
No, I mean, I really just like grab all the like available option strings and just print all of them out. And I did not look at this.
They're literally the same. It's just that the
Oh.
validation lets you put in spaces or not. Or
Oh, okay.
Yeah.
So this was not just the auto generation of the Python code. just
Oh,
runs
this is
the-
calling a method that ifback2 exposes to like give the available solver names or precondition names. Yeah.
Our attempt to find typos in Trilinos.
Okay, nice.
What else has been exposed to Python in Trilinos other than the Linux solvers?
So something that Mauro mentioned earlier was that, and that was sort of like the earlier sort of like testing ground for this work was the rapid optimization library. So that is also like it's slightly annoying because it's like wrapped in a like independent package and not integrated into PyTrilinos2 yet. So that's already exposed. If you remember like Jonathan's talk about preconditioners, what you see is missing at the moment is like Tico, which is sort of like the block preconditioners, and all the domain decomposition stuff is also currently missing. None of these things are necessarily hard to do. It's just somebody needs to go in, and typically what this does is because it really like tries to like wrap every single function, it exposes a lot of like issues in the packages themselves. So say for example, there's a method that somebody declared but never implemented. This thing will complain about that because it tries to like bind to it, and that really doesn't work well. And so more than actually like PyTrilinos2 development, it's more bug fixes in the wider Trilinos ecosystem to make sure that PyTrilinos2 can actually sort of like go through and just like grab absolutely everything and expose everything. Now you can, we can also work around this by just like blacklisting a certain amount of like things and then like getting away with the minimal sort of like interface. But if we find these issues this way, then it's also good to fix them.
You're finding valid API issues.
Oh yeah, totally, yeah. We also found like issues where like inheritance, like where like the interfaces got like slightly changed from like base class to the derived class, and the tool obviously started complaining about it, which was great. But it sort of like means that we're the point where all of these issues start hitting us, and we need to fix them. And so this is why this is not necessarily a fast process to just say, oh, let's wrap everything. If the code was perfect, then yes, that would be the case. We would just say like, okay, enable every single package and wrap absolutely everything, and then everything's great. But yeah, not quite yet. All right, everybody's happy or tired? Oh.
I was going to hold this, but
Go for it.
So you made the comment that this is a feature that we replicate what C++ Trilinos does. Why do we want to do this? I guess if you're trying to reach a new user base, why don't we be more aggressive and throw out a lot of the baggage that we have from our C++ code, which C++ people love, but Python people might hate?
Well, I think yes. Personally, I want to like move in that direction. A lot of the code that we have in C++ is just sort of orchestration, and for that, I would argue we really don't need C++. If it's just a matter of like pushing around like parameter lists and like deciding like which parameter list to give to like what subsolver of say Tico, that doesn't really need to be compiled code. And I believe that it does slow down development if every bit of code is just compiled, even the stuff that really isn't performance critical. Now, we obviously have like a long history in a C++ code base, and making that decision to like throw out a lot of stuff that people have spent time on, or like replicating that logic in a different language just because we think that it might be more user-friendly, or that it might not be necessary to have it in C++ is not really like a strong argument. But if moving forward we can develop some of our application code using Python and be a little bit more flexible and also make it easier to couple to other things. Coupling in C++ is always sort of like, it's doable, but I think it's more of a lift than like doing this directly in Python.
That's my question. There are different use cases. One is making it easier to couple to the C++ code. That's one use case. The other one is attracting the Python users that don't have any background in C++ at all. The latter case is the one that I'm worried this doesn't do it. Like I asked the question.
Right. These are still the same C++ low-level interfaces that we've always used.
Still all the packages,
I mean,
Can we be more, I guess, can we break the mold, I guess?
I mean, we could definitely like build on top of this and like expose more high-level interfaces in this way. I mean, I find it sort of hard to say like, oh, we'll like get rid of. I mean, if we just like have different interfaces right away, then it's going to be really difficult to convince a lot of people who are currently using our software to adopt this. This interface is supposed to make it easy for people who are already like familiar with Trilinos to sort of like switch gears and get into it. But I do agree that we want to probably move to something that looks more Pythonic in some ways and is sort of like more high level than what we currently have.
So,
Yes.
I mean, along those lines, we did that in MATLAB a while ago for the linear solvers, right? Where you just say, hey, it was ML at the time, ML set up, have this list of things, and it would just do a thing. ML solved, and it would do the thing. There's no reason we couldn't do that here with Python, right?
Exactly, yeah.
Trilinos set up, Trilinos solve, and then you could just abstract the entire linear solver stack away to, with some really high-level interface.
I mean, you could hide it with that, but then if somebody wants to then graduate to
Yeah, right.
Mhm.
They can do other stuff. I mean, the other thing that Malak had just brought up is the other thing we did with MATLAB is we had the ability, no one ever uses, but the ability to basically write subcomponents of Glusa in MATLAB and have it basically call that. That would be super cool from a developer perspective.
I mean, personally, I find that great, but I'm not sure that anybody else will really use this.
That was the problem. It was so witty and cool, and then Ray never used it. So,
I used it.
oh, he did it.
I did it to test an algorithm in a paper,
Yeah.
and I was able to write it inefficiently in MATLAB, and I didn't have to worry about the C++.
Yeah, and that's kind of exactly the sort of thing it was for.
Jacob.
Yeah, so with respect to Python users, one thing we are currently moving towards in PyCocos is getting rid of U. Like, no Cocos data type.
Oh,
You
you
Mm.
give us,
just NumPy research.
you give us a NumPy,
Mhm.
a PyTorch, a QPy, a whatever, because that's, I mean, you saw his reaction. That's what the people want to do. They get something from some other library. They don't want to have to deal with data types that are custom to C++ stuff. And the functions that we provide or that you provide are super valuable, but that's the thing they care about,
Mhm.
the data types. They want their own data types, or the ones that someone else gives them. They don't have to think about this.
It's actually less about the type, it's more about the interface, right?
Yeah.
I don't want to have to go and figure out what the interface for that map is and
Mhm.
stuff like that when it should be Pythonic in nature and I should iterate it, right? And it's that kind of thing. So I spent a lot of time developing for like Exos.py. And one of the things that I did when I was working on it was start making all of the things backwards compatible so that if users were already writing scripts that look like C and act like C, they could continue doing so and I wouldn't say anything. But anyone that wanted to use Python, like, I don't know, Python, could actually start using with statements and stuff like that. So like the interfaces are both there, they're just separate.
Mhm.
And that was the nice part. And the problem with that is the cost. The problem with that is absolutely the cost. Maintaining that interface is expensive because you can't generate an entire different interface out of thin air.
I mean, we're not going to be able to just like retemplate everything like on the fly for the entire like stack. So yeah.
But again, we have empty span. Maybe things get better. Some things.
Okay.
I'll just make a quick comment. Going back to Mike's question, sometimes we're uncomfortable when we go to new architectures being reliant on a lot of code. So like, if I had to port Binder to say El Capitan the first month it was stood up, that's where the worry comes in, and that's why we like the standalone C++. And so,
I mean, it is an additional dependency, and it's not like lightweight.
yes, if I had to dig in there and debug that, I'd be very worried.
Understandably, yes.
Cool, anything else? Thank you, Christian.